Well, this is really out of focus. 1, 2, 3, 4, 5, 6. Okay, this is AP1, 12, period 4. Let's focus. Okay. Good morning. Get started in about 1 minute. Okay, I think that's enough to get started. So, hello everyone, welcome. So this week we're talking about musical instruments. And so I wanted to review what we discussed last time. So last time we were talking about stringed instruments. Okay. And so stringed instruments have a couple of possible standing waves. So I'm just going to draw the first 3, I think. So if this is the ends of the instrument, when you pluck the string, there are a number of different standing waves. So here's one of the standing waves. That's called the first harmonic. So this is n equals 1. The second harmonic looks like this. Okay. And the third harmonic looks like this. Okay. And so when you pluck a string, you are creating a superposition of all of these different harmonics. Okay? And usually it is the first harmonic when you pluck the string that has the biggest amplitude. Okay? So for that reason, even though all of these harmonics have different frequencies, the one with the biggest harmonic is what you perceive as a musical note. Okay. So then we said that the instrument has a length L, and so we went through this derivation where we said that the wavelength of the nth harmonic is 2L over n. Okay. And then we used the equation V equals lambda F to then convert that into a frequency. So the frequency of the nth harmonic is NV over 2L. Okay, so here N is the harmonic number, V is the speed of a wave on the string, and then L is, of course, the length of the vibrating portion of the string. When we were talking about these standing waves, I also introduced the idea of nodes and antinodes. So a node is a part of a standing wave where the medium is not being displaced. Okay, so the ends of a closed instrument are always nodes because the ends are pinned down. But then also there are some nodes in the middle of the string. So for example, right here and right here, where it's kind of, it's like the medium is doing this, and you can see the point where my fingers touch isn't really moving. Okay, so these are all nodes. All right, and then in between two nodes, there's a spot where the medium is vibrating a whole lot. Okay, and so those places are called antinodes. So nodes and antinodes, it's a useful concept. So one of the things I wanted to talk about, we also talked about factors affecting the wave speed. Okay, so if you have a musical instrument like a ukulele, the first factor is the thickness and the density of the string. Okay, so the density of the string. So you can have strings that are made out of steel, you can have strings that are made out of nylon, you can have strings that are thick, you can have strings that are thin. So all those things are going to affect the wave speed and hence the frequencies that that particular note can play. And then the other thing is that can affect it is the tension on the string. Okay, so that is basically turning the peg and changing the tension in the string. More tension will result in a higher wave speed, which will result in higher frequencies being played. One interesting thing about stringed instruments is that the tension in the string also depends on temperature. So if so let's say I tune this instrument in my house where it is 75 degrees, okay? Then I take it outside into the winter where it's like 30 degrees or something. So because of the reduced temperature, the strings are going to want to shrink. They contract, okay? Most materials, when they get cold, they contract. And so the string is trying to contract, but it can't because it's being held at both ends. And so what that does is it will raise the tension in the string, which will cause the instrument to then have a different wave speed, which will take it out of tune. So if you take an instrument from one environment to another environment, that can affect it. Another thing that can affect it is moisture, because if the if the material that the instrument is made out of absorbs moisture or or dries out, it can affect the length of the instrument slightly. Okay, so for example, if you get a piano, they'll say wait a couple of months to have it tuned, or I don't know if it's a couple of months, maybe it's a couple of weeks, to have it tuned because when you put the piano in a new environment, it's either drying out or it's absorbing moisture given the climate that it's in. And so, it's pointless to tune it too early before it has adjusted to its new environment. Okay? So, let's go ahead and do an example with this. So, let's suppose that a stringed instrument is, let's say, 0.6 meters long. The wave speed on the string is 600, or not 600, let's say 530 meters per second. Okay. Calculate the frequency of and draw the seventh harmonic. Okay, so calculating the frequency is really easy. So we're trying to get the frequency of the seventh harmonic. Okay. And so the frequency of the seventh harmonic is going to be 7V over 2L. So plugging in the speed is 530. And then the length of the instrument is 0.6. So that frequency is going to be 3,092 hertz. Okay? Now keep in mind that you probably wouldn't hear that frequency. Okay? Because most of the time you hear the first harmonic. Okay, so you would hear it, but it would be sort of more adding to the qualities of this particular stringed instrument. All right, so now we need to draw the harmonic. Okay, and so harmonic, I called these little vibrating portions of the string, I called them footballs. That's not a technical term, but you can see that the harmonic number is basically counting the number of footballs. Here we have 1 football, here we have 2 footballs, here we have 3 footballs. All right. And so the 7th harmonic, by extension, is going to have 7 footballs. So I'll draw 7 footballs. 1, 2, 3, 4, 5, 6, 7. So that is what the, so then I'll draw the other part of it. 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. And so you can see that this has 7 nodes. Actually, not 7 nodes, 7 antinodes, because there's 7 footballs. Each football is an antinode. And it has 1, 2, 3, 4, 5, 6, 7, 8 nodes. All right, so that's an example of one of these questions. So now what we're going to talk about for the rest of today are wind instruments. Okay. Wind instruments. So these stringed instruments, I will often call them closed. So in the quiz today, I call a stringed instrument a closed instrument. Closed meaning that it has a node at each end. Okay. For wind instruments are usually a tube of some kind. So I will draw the tube like this. Okay. So it's kind of like you're looking at the tube from the side, so it looks like a rectangle. So this is what I would call an open instrument because it is open on both ends. So there are instruments that are like that. There are musical instruments that are open on both ends, and the wind vibrates, or the air vibrates inside it. And then you also have what are called open closed instruments, which are open on one side and closed off on the other. Okay, so a lot of wind instruments are either one type or the other type. All right. So for wind instruments, the medium is the air itself. Okay, so in other words, the wave speed is going to be the speed of sound, the speed of waves in air, which is the speed of sound, which is around 340 meters per second for air. Okay, you could take a wind instrument and fill it with some other gas to change its frequency. That's essentially what's happening if you slurp helium. Okay, if you slurp helium, you are filling your lungs with a gas that's not air and has a different speed of sound. It happens to have a higher speed of sound. And so that's the reason that your voice sounds higher pitched when you slurp helium, is because it has a higher speed of sound. Helium is a lighter gas than air, so sound travels faster through it. Okay, but if it's just filled with air, it's around 340 meters per second. Again, temperature affects the speed of sound, and so, if you have a wind instrument that's tuned and you take it to a room with a different temperature, it can go out of tune. Also, wind instruments need to warm up, okay? Because if you have a really cold instrument, then the instrument is going to cool the air inside it, which changes the speed of sound inside the instrument, okay? And then as you hold it, it warms up, and so these differences in temperature can cause the instrument to go out of tune, okay? So you kind of like want it to settle into its temperature that it's going to have in its environment, and then tune it. Okay, so I'm going to start off with an open instrument, okay? And then we'll go to closed, or open-closed, excuse me. So for an open instrument, open instruments have antinodes at each end. So whereas a closed instrument has nodes at each end, open instruments have antinodes at each end. Okay? So we can just go through and we can draw the harmonics. Okay? So it turns out that the first harmonic you can draw kind of looks like an hourglass. Okay? Looks like that. So here it has an antinode here and an antinode here, and then there's a node in the middle. All right? So this is the n equals 1 harmonic, the first harmonic. So again, just like with closed instruments, to go to the next harmonic, you add a football. Okay? You add a football. So, but here, you can't add a football at the end because it would be weird to have something that looks like this where you have the first harmonic and then you add a football like this. That doesn't make sense. So what you do is you insert the football into the middle, okay? So to go to the next harmonic, I would insert a football into the middle. So it looks like that. Okay? So that is the second harmonic. All right. Then to go to the next harmonic, I would insert another football in the middle. So it's going to be that. So here I have no footballs in the middle. Here I have one football in the middle. Here I have two. So this is the third harmonic. And I'll draw one more. Okay. So there's the fifth or the fourth harmonic. So now I have three footballs in the middle. Okay, so there we go. Now, if we do the analysis, so if you remember what we did last time, we counted up how many waves there are in each case. All right. And so, for example, this right here is half of a wave. Why is it half a wave? Because we have half of a trough and we have half of a crest. A complete wave has a full crest and a full trough. This wave only has half of a trough and half of a crest. Okay? So that's half a wave. This right here is a full wave. Okay, why? We have half of a crest, and then the other half of the crest is over here. Okay, and then we have a full trough in the middle. All right, so this is a full wave. All right, here we have half of a crest, we have a full trough, and then we have the other half of the crest. So this would be a full wave, that distance right there. Here we have half of a crest, we have a full trough, and then we have the other half. So this is going to be a full wave, etc. Now, I'm not going through this very carefully because if you work it out, it's the exact same formula. So for open instruments, you have the exact same formula. The wavelength of the nth harmonic is 2L over N, and the frequency of the nth harmonic is NV over 2L. All right? But a main difference is that this V, so here in this formula, the V was speed of a wave on a string. Okay? Here, the medium is the air itself, so this is the speed of sound of the gas filling the instrument, which most of the time is going to be air, okay? But it could be some exotic gas. In fact, I think on the quiz I might have one with an exotic gas. All right. So let's do an example with an open instrument. All right. So let's suppose an open instrument is, let's say it is 0.35 meters long, 35 centimeters long, and filled with air. You play the instrument. What frequency is heard? Okay, so first of all, because I didn't specify a harmonic number, I said what frequency is heard. So the fact that I'm asking that, as I said, it is the first harmonic that usually has the biggest amplitude. So in the absence of more information, we're just going to assume that you hear the first harmonic. Okay? So n equals 1. So what you would do then is you would say the frequency of the first harmonic is 1 times V over 2L. It's filled with air, and so air has a speed of sound equal to 340 meters per second divided by 2 divided by 0.35. For 85.7. So 486 hertz would be the frequency that you hear. Okay? So pretty straightforward. So now what we're going to do is we are going to talk about open-closed instruments. And we're going to go through the same process. So open-closed instruments, they have a antinode at one end, and they have a node at the other end. Now you could ask the question, well, is there a closed open instrument? And the answer is that's the same thing, right? If you have an instrument with an antinode at one end and a node at the other end, well, guess what, folks? Now it has a node at one end and the antinode at the other end. Okay, so open, closed, and closed, open, same thing, just looking at it from a different side. Okay. So Um, Typically, I will draw an open-closed instrument like this. Okay, so kind of like a tube, and it's closed at one end. So I would say most wind instruments are open-closed. So for example, a flute is capped off at one end. So flute would be an open-closed. You have, what else? You've got um, trumpet. Trumpet is open at the end with the horn, right? Horns are open closed instruments, right? Because you are have the horn end, and then the instrument is closed at the other end where your mouth is. Okay, so your mouth is kind of the back end of this instrument, etc. Okay, so let's go ahead. So the length of this instrument is L, and this one has a different formula, so we have to go a little bit carefully here. All right, so the simplest wave, the simplest standing wave that I can draw with a node at this end and an antinode at this end, it looks kind of weird. It's like just that. Okay. So, what is the wavelength of this? Well, if we look at this, this is half of a crest. A full wave would have the other half of the crest and then the full trough. So this is actually a quarter of a wave. All right. So if I want to know what is the wavelength of this, I have to multiply the length of the instrument by 4. So 4L is going to be the wavelength, which I'm going to write in the suggestive form of 4L over 1. Okay? To go to the next harmonic, what we do is we add a football. Okay? And so I'm going to add a football to the left end of the instrument. So I have a football, and then like that. All right. So that is the next harmonic, and I'm saying next harmonic intentionally. So if we look at this, we've got a full crest and we've got half a trough. So if we want to finish the wave, we have to add the other half of that trough. Okay. Now, so this is adding basically another third of a length to the instrument. All right. So the wavelength of this harmonic is 4L over 3. All right, because we added a third. So 1 plus 1/3 is 4/3. All right. To go to the next harmonic, we add a football to the left side. So we have 1 football, 2 football, there. So to go to the next harmonic, you always add a football. And so I can see that this instrument is sort of naturally divided up into 5 sections, okay, of equal size. And a full wave takes up 4 of those sections. Okay, so the instrument is divided up into 5 sections, and a full wave takes up 4 of those. So that means that the wavelength is 4L over 5. Okay. To go to the next harmonic, I would add a football to the left side. So that. All right. And so I can see again that the instrument is naturally divided up into 1, 2, 3, 4, 5, 6, 7 parts of equal size. And a full wave is 1, 2, 3, 4 of those. So 4/7 the length of the instrument is a full wave. Okay? So you can see that this continues. So there's obviously a pattern, all right, which is that the wavelength is 4L over N. So the wavelength of the harmonic is 4L over N. But here's the thing, when you're talking about open-closed instruments, is that we don't have a second harmonic. So this is the harmonic number right here, okay? So N must be odd for open-closed instruments, okay? So if I asked you a question where I was like, what is the frequency of the second harmonic of this open-closed instrument, you would say the second harmonic doesn't exist because 2 is an even number, okay? So that's an important point for open-closed instruments, okay? And then for the frequency of the nth harmonic, once again, we do this, we use the equation that V equals lambda F, and we can use that to solve for the frequency. What you get is NV over 4L. Okay? So what are the takeaways from this discussion on musical instruments? And by the way, what we're talking about has nothing to do with drums, okay? What we're talking about are instruments that are essentially one-dimensional, right? A string is one-dimensional, okay? If you were on this string, you can only go forward or backwards along the string. A flute is essentially a one-dimensional tube, okay? But if you think about a drum head is two-dimensional, right? You can go forward and back and side to side along the drum head. So drum heads are a lot more complicated, okay? So we won't be talking about those. But the main takeaways are you should be able to draw the nth harmonic. You should be able to calculate the wavelength of the nth harmonic. And you should be able to calculate the frequency of the nth harmonic for closed-closed, open-closed, and open-open instruments. Okay? And so I think that you can probably do that. So I'm going to stop my lesson here. All right? I'll see you in the Zoom room.